Alright, so this is the second edition of Admiral Science dealing with the periodic table. Again, I'm your host, Mr. Allen, and this is 8th grade physical science. Alright, so this is what we should already know before we head into our periodic table. We discussed that the atomic number is the same thing as the number of protons, and we also discussed that the letters, the two letters or the one letter that you see on the periodic table, that is the element symbol, and that the atomic mass is the combination of protons plus neutrons. And in case we do not remember our equation that we discussed before, P plus N will get us AM. Alright, so remember this is our protons, which is found here, and our neutrons can be determined by either subtracting these two protons and the atomic mass, or the atomic mass from the atomic number will get us the protons, but to find the atomic mass, protons plus neutrons will get us our atomic mass. Alright, let's start off with our periodic table. A little bit of history. This guy is Dmitri Mendeleev. This is his first idea of the periodic table. He even predicted some future elements that we may have, but as you can see, it does not contain all the elements that we now have today. But this is what we started off with. He gave us the groundwork, the framework for the periodic table. Alright, now this is what our periodic table looks like today, and with a few more additional elements added. As you can see, it's broken down into certain categories. It has some numbers at the top, sort of like what Mendeleev had, and it's broken down into three distinct categories. We see some blues, we see some purples, and we see some yellows, and we'll get to what these each mean in our next couple of slides. Alright, the first thing that we should mention is that the periodic table has groups, distinct groups. Alright, so we have a total of 18 groups. We have, this is group 1, we have group 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. Alright, so we have 18 distinct groups. These groups are the columns of the periodic table from 1 to 18. These right here are embedded within groups 3 through 12. For 8th grade science, we will not particularly focus on transition metals, which is what these are right here. But for 8th grade science, we do need to know the groups, and the groups are the elements in the same column. And these groups, they will have some of the same chemical bonds, or they'll have some, they'll react the same. All right, they will typically react the same with the elements of the same group. All right, so what does groups tell us? Groups tell us precisely what the valence electrons are, and as mentioned before, our valence electrons are very important in determining our chemical bonds. All right, so let's see. We're going to look at the element lithium. Lithium is located in group 1, and lithium has an atomic number of 3 and an atomic mass of 6.9. Alright, so we're going to construct our Bohr model. Remember, our Bohr models tell us the number of electrons, as they are important in chemical bonds. So let's make a Bohr model for lithium. Alright, so here we have lithium, and we know from our atomic number that lithium has 3 protons. And we can also determine the number of neutrons, because this is, if you round 6.9, it rounds up to 7. And remember our equation, P plus N equals atomic mass, and we know our P, which is 3, and our atomic mass, which is 7. So now we can determine the number of neutrons, because 3 plus what would get us 7. And if you said 4, you are correct. We have 4 neutrons. So 4N. Alright, now we have our nucleus. Now let's get our electrons. And we know our electrons equal the number of protons in a stable element. So let's begin with our first orbit. Our first orbit can hold up to 2 electrons. So let's go 1 and let's go 2. Alright, now that we have 2, we only need to plot one more. So we have to draw another orbit and plot our last electron. And we're going to plot it here. Alright, so now we have 3 electrons plotted. Now the electron that's on the last shell, the last orbit, that is known as a valence electron. Alright, because it's on the last level, if we had 3, 4, 5, however many we have on the last level, those are our valence electrons. And because lithium is in group 1, it is expected to have only 1 valence electron because it's the one on the outside. This same thing applies to sodium, which is Na, potassium, which is K, Rb, rubidium. All the elements in group 1 have 1 valence electron. No matter how many orbits they may have, they still will have 1 valence electron because they should have 1 electron on the last level. Alright? So our groups tell us the valence electron. If we are in group 2, that means that there has 2 valence electrons. And here is the kicker. Alright, so if you skip, remember in 8th grade, we're not going to really focus on transition metals too often, but if you skip elements 3, if you skip groups 3 through 12, and go to 13, to determine the number of valence electrons, it wouldn't be 13, 14, or 15. Our valence electrons would then be simply the second digit. So for example, elements in group 13, they have 3 valence electrons. Elements in group 14 have 4 valence electrons. Elements in group 15 have 5. Elements in group 16 have 6 valence electrons. Elements in group 17 have 7 valence electrons, and elements in group 18 have 8 valence electrons. Now, the exception to this rule is helium. Helium, because it has an atomic number of 2, only has 2 electrons, and so its valence electron number is 2. It's complete. Alright, so all the ones on this last row, 18, have complete shells. And when we say complete, that means their electron number is full. And I forgot, I cannot write past this point right here, but their electron shells are full. No matter how many periods they have, their electron count is full. And that's what all the other elements want. They want to be like group 18. They want to have a complete shells of electrons. But right now, only group 18 are complete. So helium, although it only has 2, the maximum for its orbit is 2. So it has a complete shell. Now, then we break down our elements into periods. And periods are on the side. They're the rows. They're 1, 2, 3, 4, 5, 6, 7. These 2 that are broken off from the periodic table, these are a part of group 6 and 7. Notice their color. This one is blue and this one is purple. They're still together. Alright, and what our periods show us is that all the elements on a certain period, they will have the same number of orbits. So for example, let's go back to lithium, and we say that lithium has atomic number of 3, atomic mass of 6.9, round that up to 7. When we make our Bohr model of lithium, as we refresh, we said that 3 protons, 4 neutrons. Remember that 7 should equal that number right there. When we make our Bohr model, so we have our first orbit, which contains 2 electrons, and then we have to draw one more because we got to get 3, and that first orbit only hold 2. And then we have one more electron. That's our valence electron. But what periods tell us is how many orbits. So if you notice, we have 1, 2 orbits. And if we look at lithium, lithium is in period 2. So because it's in period 2, it should have 2 orbital shells. So 1, 2. Alright, so this number of the period says how many orbital shells, or the circles you draw around the nucleus, how many should each element have. So all the elements in period 2 have 2 orbital shells. All the elements in period 3 have 3 orbital shells. All the elements in period 4 have 4 orbital shells. So if we go back, let's look at helium. Remember, helium is our... For some reason, it will not let me erase on this slide. Let's see, I'll take off the arrow. Okay. Alright, so let's see. If we look at helium, if we look at helium, helium is in period 1 and group 18. Alright, now period 1, group 18. So if we answer this correctly, remember the exception to helium about group 18 is that instead of it having 8 valence electrons, it has 2. And we're about to see why. Because if you notice, it's in period 1, which means that it only has 1 orbital shell. And because remember, our maximum for the first orbit is 2. It cannot have no more than 2 electrons. Helium, because it has 2 electrons, will only have this first orbit to complete, and then that's it. So helium's an exception. It has 2 protons and 2 neutrons because it has an atomic mass of 4.003, which rounds out to simply 4. So that number should equal 4, and then we have our 2 electrons on the outside. And so it has 1, it's in period 1, so it has 1 orbital shell, and then it has 2 electrons, and it's complete. Alright, so that is periods. So again, our groups tell us the number of valence electrons. In case we can't remember, valence electrons are the electrons on the last level. Alright, and our periods, which we have 7 total periods, they tell us how many orbital shells we need. So for helium, it's in period 1, it only needs 1 orbital shell. All the elements in period 2 have 2 orbital shells. 3 have 3, 4 have 4, 5 has 5, 6 has 6, and 7 has 7. Then we go into categories. Alright, our periodic table is broken up into categories. We have metals, non-metals, and metalloids. Alright, as you can see, most of our metals, most of our periodic table is metals. And our periodic table shows that we break our elements into categories, and then we have an in-between category. And we'll talk about that in-between in a second. But first, let's look at metals. Alright, metals comprise most of our periodic table. And metals have certain properties that make it valuable. For example, it is shiny. Alright, we know that most metals are shiny, and we also know that it conducts heat and electricity well. So if we have a pot on the stove and we heat it up, what happens? If you touch the pot, it's hot, correct? Alright, the same thing if you use electricity. If you have a metal pipe and you touch electrical wire or something, guess what happens to you? You get electrocuted along with the pipe. So it conducts heat and electricity well. Most metals are solid at room temperature, as we know. We have copper, lead, tin, nickel, and many metals are malleable. And this word right here, malleable, means that you can mold it, transform it with force. All right, you can mold it, transform with force. Like many of the metals that you see that make up the utensils you use, or the necklaces people wear, it has been molded. It has been hammered and molded into a particular shape specifically so that you can use it, such as a lock. Alright? So metals are malleable. And some metals are ductile, which means they can be formed into wire, like up here with the copper wire. Alright, this copper wire is ductile. It has been formed into a wire. Alright? Now, our nonmetals are located in this section of the periodic table. And our exception over here is hydrogen. It is located next to the rest of the metals. Alright, so hydrogen is the lone nonmetal on this side, but then most of our nonmetals are located over here. Alright, properties of nonmetals. They are poor conductors of heat and electricity, which means they do not conduct heat, or they don't transfer heat very easily or electricity very easily, which makes it a good thing. That's a good property to have when you need to work with electrical equipment, or you need to work with equipment that gets hot. They prefer you to use something that does not conduct heat or electricity very well. And then nonmetals are dull and brittle. As you can see, it's not nearly as shiny as metal, and brittle. And remember, like with the piece of chalk, if you crush a piece of chalk, chalk is made primarily of carbon. When you hammer chalk, what happens? It breaks, it shatters, it turns into dust. That is brittle. It means that it is easily broken. Alright, and that is what makes chalk easily breakable, because it's made primarily of carbon. Alright, and lastly we have metalloids. And metalloids are our in-betweens. They contain properties of both metals and nonmetals. They're great because they're a hybrid. They contain some of the best qualities of both, like such as certain metalloids that are used for semiconductors in computer chips. Because remember, you want things, if it has heat or if it contains heat, you don't want it to overheat, and so you use these semiconductors so that the chips do not overheat in the computer and causes a fire or something. So you want to make sure you have that in-between quality, and that was making metalloids so important. So metalloids have some properties of metals and some properties of non-metals. Some metalloids are used to make semiconductor chips in computers, as I just said. So silicone is one of these metalloids, and it's right there. If you notice, on most periodic tables, there's a zigzag line, and the metalloids fall on this zigzag line. Alright, they fall right here on the zigzag line. So we start off with boron here, and we got silicone, germanium, and so on. So all the ones on that zigzag line that you'll find on your periodic table, those are where your metalloids are located at. And if you have any questions, you are more than welcome to review this lesson again. And just to recap some things, our periodic table is broken up into categories: metals, nonmetals, metalloids. And also it is broken up into groups, which are the columns, and periods, which are the rows. Alright, our groups let us know the number of valence electrons from 1 to 8 using groups 1 to 13 through 18. And then our periods broken up into allow us to know the number of orbits around the nucleus. So 1 orbit, 2 orbits, 3 orbits, 4 orbits, 5 orbits, 6 orbits, and 7 orbits. And if you have any questions, please do not hesitate to leave a comment in the comment section below, or you can simply write it down and ask me tomorrow. Be sure to look out for our next video, which will be on chemical bonds and valence electrons. This has been Brendan Allen with the periodic table. Thank you.